Hello, Dr. Charity.
Good morning. Okay, I'm looking for my screen. Sorry. Yep. Good morning, everyone. You can hear me and you can see my screen, right?
Yes, we can hear you, and we see entropy S and the second law of thermodynamics.
Good. Thank you. Okay. So today we are looking at the concluding part of our chapter 11, which is using energy. And we'll be discussing majorly. There's practically no calculation in today's class. Everything is just discussion about how we make use of energy. Okay. So we've seen in our last class, the first law of thermodynamics, the first law being the description of conservation of energy, where we said the change in energy of the system is equal to W plus Q, which is work plus heat. And we also used the description of the second law to explain efficiency. So we'll be looking at what exactly the second law is, and we'll also be looking at entropy. Now, the reason why whenever I would discuss the second law of thermodynamics and we make mention of entropy is because the second law of thermodynamics is described in terms of entropy. Okay, and the symbol for entropy is S. So we want to look at these two majorly today, and also by extension, see how they apply to the systems of life. That is how we use energy as human and how we also apply that in technology. So before we go further to describing what the two terms are, we'll start by first understanding what is reversible and irreversible process. We also already know what it means because we've come across these terms in several fields. Simply put, reversible processes are those processes that can be restored to its original state. They are such that when it happens, it can go both ways, can go both forward and backward, and they will look as if nothing has changed. Okay, I'm just giving a description. An example of reversible process that I want to look at in this discourse is that of the molecular collision. So we see the molecules, the atoms there. This, just a moment. This and this. There are two atoms heading in the opposite direction, and when they collide, they have the parts like this. You see, nothing actually changed apart from their change in direction. Okay, and if you reverse the process as well, you have a similar action and output. So it's going both ways. You can take it forward and you can reverse it to its original state. Now we'll see another example that describes the irreversible process, that is process that cannot be reversed. Let's look at the image here of the car hitting the wall. You notice that once the car hits the wall, there's a kind of crash on that car. It crashed into the wall. Now, look at image 2. Is it possible for this crashed car to go back to the original state as if nothing happened and change direction? No, it's not possible. And that's why we said this is physically impossible. Now, the only way to return this to its original state is after the crash, they'll have to take the car for repair, fix so many things. So what we're trying to buttress here is that reversible process happens like almost immediately. You can return it to its original state. It's not like this kind of reaction where after it happens, it cannot be returned unless you have to put in a lot of repairs work to return it to its original state. Doing that is not a reversible process, okay? So we'll have repairs, we'll have to manage, put in extra items or materials to make it look like its original state. But it's never going to look like its original state because it's not going back to the exact state it started, okay? So irreversible processes are majorly processes that cannot be reversed back to their original states almost spontaneously, okay? So that's the concept we'll be using to describe the entropy, right? And another point also that will be seen in entropy, because entropy is basically the, or put in a simple way, the spread of energy in a system. But we'll be defining that scientifically using the appropriate term. But we want to also look at what we mean when we want to describe entropy and we use the term thermal energy spread. It's simply the movement of energy, distribution of energy in that system. That's what we mean by thermal energy spread. And we're referring to the energy, temperature energy, the energy change that relates to change in temperature of a system. So we'll have several ways that energy can be distributed in a system, okay? We'll have the one we saw in our last class here, how that energy moving from the hot, this place will have several molecules, right? The description we saw the last time. The ones on the hot side will have the high kinetic energy, and then they will impact it on the molecules in the low side to bring about the transfer of heat until it gets to a stage where the temperature on both compartments becomes equal. Okay, and we have always emphasized that the thermal energy process is irreversible. It cannot be returned to its original state. You cannot, from this system, achieve this again. But once it happens, it goes. So that's why some systems, when we say energy loss in a system, we're just simply saying the energy that is converted or the energy that has been transformed to thermal energy, because you cannot return it back into that system. It's gone, it's gone. Okay, but it's not practically lost. We have advanced method of converting thermal energy to other forms of energy, but we're not looking at that now. But basically, in terms of its spontaneity, we cannot reverse thermal energy. All right. So for this part of the diagram here that I want to use to describe the distribution of thermal energy in gases, we see that the molecule of the gas, we see this particular molecule, it has kinetic energy. Look at the others, they are just, they have little on kinetic energy that is not noticed. The molecule that has or that have received kinetic energy transfers or heats, imparts the other molecules, and then it transfers. The one that is heat imparts another one. They keep imparting each other until the kinetic energy that is coming from the thermal distribution, the kinetic energy converts to several thermal distribution on each of these molecules. And that is what we now have here. Okay, we now have that both gas systems will have a total of the same energy as we have said in the case of first law of thermodynamics, because the kinetic energy here has been distributed, and then the thermal energy distribution is on each of the molecules. Okay, it is the same thing that is happening here as well. All right, gradually transferring the energy until the whole system is at equilibrium. They have evenly distributed thermal energy. Okay, so without understanding, we want to quickly specify what entropy is. All right. We use the word entropy to quantify the spread or dispersal of thermal energy. Okay, basically when we say entropy, we are describing, I know that we used to say is the degree of disorderliness in the system. Yes, but what we mean actually by implication is the measure of the spread or dispersal of thermal energy throughout the system. Okay, and a system that has energy concentrated that is not spreading will have a very low entropy. But a system that the energy is spreading out will have a high entropy. Okay, so we just use that to quantify the rate at which thermal energy will spread in a system. Now, the entropy of a system will come to its maximum point when that system is in equilibrium, as you can see in this case. This is the maximum point where both of them, there is no longer exchange of heat or spreading. They all now have even temperature. So we say this system is at equilibrium. The entropy of that system is at its maximum. Okay, as long as there's room for transfer or change in the energy of a system, the entropy has not reached its maximum. So it will reach its maximum when all is equal, or the temperature on that system surface is equal. So we use the second law of thermodynamics in terms of, in the language of entropy. So let's see the definition of the second law of thermodynamics as it applies to using energy. Okay. So the second law, simply put, says the entropy of an isolated system never decreases. The implication of this statement is simply that the thermal energy process is irreversible. Okay, so it's never going to go back to its original state. So if the entropy is not yet at its maximum, or the system has not reached equilibrium, it will keep increasing. But if the description of the entropy started from when the system is maximum, it remains so. It's not going to drop. It cannot go down. So this definition also emphasizes this, which I've already said earlier. Entropy is at maximum when the system is at equilibrium. Okay, we should take note of this word because we'll keep buttressing on it, explaining or expanding it to applying the use of energy. That the entropy of an isolated system never decreases. Note the word isolated. When we described or explained the first law, we're describing it in terms of a system that interacts with its environment. It's gaining, it can lose heat, it can gain heat, there will be input of work done, output of work done. But in this case, for the second law, our focus or definition or understanding of the distribution is in reference to isolated system. That does not mean this law does not describe systems that interact with the environment, but on a certain rule as well, or principle. Okay. So generally, thermodynamics, we have seen the two laws of thermodynamics now. We have seen the first law that talks about energy conservation. And we have seen the second law that simply talked about the spread out of that energy. And when we talk about energy in thermodynamics, we are only referring to thermal energy. So thermodynamics is basically the science of energy, understanding the science of thermal energy in terms of conservation, distribution, and application to technology. Okay, so if we want to summarize the two definitions so far, it's going to be the first one saying energy is conserved, it can be transferred, transformed, but the total amount does not change. This is simply the conservation of energy principle. It's not created nor destroyed. It can be transformed, but the total remains the same. Okay. Why for the second law, the emphasis on the spread of energy, an isolated system evolves until the thermal energy is maximally dispersed among the system's constituents. As we saw in the first two diagrams, where we have the molecule, one dispersing the energy one after the other until the system entirely have the same thermal energy. Okay, so this basically is a summary of what thermodynamics is. Okay, so we'll look at phenomena and then highlights on how we use second law of thermodynamics to explain the statements. Now let's look at the phenomena one or scenario one. When the heat energy spontaneously flows from hot to cold, which is the natural process or direction of heat energy. What does second law say about that phenomenon? We see this phenomenon mostly dominant in the first law, and then we apply it to the second law in terms of entropy, which is the dispersal process. Now, the second law, we have this described as that when two systems at different temperature interact, as we saw in that hot and cold bus, the heat energy is transferred, note the word, spontaneously from the hotter to the cooler system. It never goes in the reverse. It's not going to go from the cooler to the hotter. The only way to make heat go in the reverse, that is go from the cooler to the hotter, is by introducing an external energy, which is, as we've seen in the previous, electrical energy, to pump out heat from the cold to the hot part, because this is not the natural route. It's like the water flowing uphill, okay? Doing something that opposes the natural process. So we'll look at the second scenario. Entropy consideration limits the possible efficiency of a heat engine. When we discussed the last time on heat engine, we mentioned something about the fact that the total heat or energy in that system cannot be used to produce work. We cannot say the heat engine is functioning at 100% efficiency. So we can only work on increasing efficiency in the terms of, the formula for efficiency, what you get over what you put in or what you pay. In terms of maximizing your gain or your profit, that is maximizing what you get. We use the example of the incandescent bulb and the bulb, that's the one we call the energy saving bulb. Because you put in little energy, you get almost triple what you get from the incandescent bulb. So the position of second law of thermodynamics to this is that it is not possible to make an engine to convert its total thermal energy to useful work done. It is not possible. So it agrees with these phenomena as stated in the first law, but it's going to be discussing or stating second law is going to be expatiating on its own fact using dispersal of energy as the focus. So the same applies to the next phenomena, which is it takes energy to move heat from cold to warm object, which we have seen earlier, because we will require external electrical energy to do that as it functions in the heat pump, to move an object from the cold to the hot. To do that, you must use an external energy input. So you see us write the equation or put the formula work input that will yield that exchange. Okay, so the last is the entropy of an isolated system will never spontaneously decrease. I've explained the issue about decreasing. You see the word spontaneous there. It simply means that if you take after the process has happened, you can actually, like that of a car, bring in external energy, bring in external materials to try to restore it to its original state, or apply or recover the thermal energy to convert to other forms of energy. But it can never be spontaneous. It is not within a short time. Okay, so it cannot just go back to its original place. So it brings in the factor of the time. So the time direction in which the entropy of an isolated system increases is going to be the future. So science is still open to discoveries. There's still research that's still going on how to be able to spontaneously or close to spontaneously apply or harvest thermal energy to application or change to other forms of energy that will bring about improvements in technology. Okay, so we now have at least a basic understanding of what the two laws are about. So now let's reason in terms of entropy. We've already talked about it, that entropy is actually that which quantifies the dispersal of energy, and the second law is just talking about dispersal of energy. If we have a system, as we can see in this figure, that has its molecule on one side, because we have several ways that we can increase the entropy of system, one of which is the one we've seen. When you increase the heat, the thermal energy will increase, and that will lead to increase in kinetic energy. We set the molecule in motion, and they will transfer the energy gained to the molecule that is cooler. All right, so that way energy is dispersed. But in this case, how do we then transfer energy without, or when there is no change in temperature? Is it possible? Yes, because change in temperature is just one of the ways to increase the spread of thermal energy in a system. So if we have a system with the molecule, see the same gas molecule, but this one, the gas molecules, they are compressed to one side. If you remove this bar, the molecules spread out. There's a gain kinetic energy, which will bring about a thermal energy increase, and they spread out. They disperse faster, which increases the entropy of that system. Entropy is the disperser. Okay. In this diagram, the entropy here is higher than the one here because of the dispersal. But if you want to reduce the entropy in this system, you will not need to pull up this. You have to bring in another object, like press on this piston to compress the gas. Because once we said it's irreversible. Once you remove this and they disperse, you cannot just compress it back. Okay, they have to be used up to that level. So you put your piston at that, you cannot just achieve this again. So this is one of the ways. Yep.
So I just wanted to check if I'm thinking about this the right way. So it would be like if you say had an empty water bottle, just had air in it, and it was like closed, so it had the lid on it. And if you squeeze it and like compress it, so it would have lower entropy, but then when you let it like go back to without the compression, it would have a higher entropy.
No, if I understand you clearly, you have a water bottle, there's space, let's say it's half full, you squeeze it and it appears like the bottle is full, and then you open it. Is that what you mean?
No, like if the bottle was empty and it just had air in it, and you squeezed it and it like had the lid on, so you like compressed the air inside, that would have a lower entropy because it's compressed, and then when you released it again, it would have higher entropy.
Yeah, it spreads out.
Okay.
When we talk about the air in it in terms of the molecules in it, okay?
All right, I just wanted to check, thanks.
Okay, so that's the idea of the ways we can decrease and increase entropy. Now, but we said something about an isolated system. That's what I thought you wanted to ask me about. We said it cannot decrease. And now we have a system that looks like it's isolated. We are saying we can compress or decrease entropy in it. Are they the same or different? Yes. Now, the fact that this system has boundaries does not mean it's an isolated system. It does not mean it's not interacting with its environment. So isolated systems are simply insulated systems that will stop or inhibit interaction with its environment, okay? So let's look at system energy and entropy. We have seen entropy, which is not going to change that's why our focus is just going to be on the energy. We have seen system as well, and we have seen energy. How does this three play out in the full process? So we want to consider again the heat engine. The heat engine we have seen before is the one that will have the hot reservoir with the QH and the QC and the heat flowing naturally from hot to cold, and part of it taken to do some work. Okay, so the work output does not change the entropy. This is already a system, but beyond this flow of heat energy is also a system put here to do work such that the entire heat engine is regarded as a kind of closed system, because it's a process that will be repeating itself over and over. So we can actually define what happens here at a particular time, what happens here at a particular time, and get a total of what is happening when it goes full circle, right? So we can tell the entropy of the engine increases or decreases at various points, because this will be losing heat, this will be gaining heat. So entropy will be increasing here. But we know that at the full circle, there's actually no change in the engine's entropy, because it has been programmed to work that full circle. That is what we mean by a closed or isolated system, and the entropy in that system will not decrease, it is defined. So it can fluctuate at different points, just like you have in the piston of the car engine to produce high speed, low speed, but optimally at full circle, the entropy remains the same, okay? So we can only make most of the heat engine by, like we said earlier, maximizing the efficiency of that engine. That is making it to give us higher output with little input, okay? So most efficient possible heat engine is one that has zero change in entropy. You design it such that, because change in entropy is going to cause a loss or a kind of, yes, releasing heat, losing heat in forms of thermal energy. So such that you can have a random or unchanging total of entropy. And that is what helps to increase the efficiency to yield a better or a higher output. No, emphasis will be on output. We want to get the most of that system. So that is how the system relates with entropy, and energy is the flow. The whole engine is the system. The energy, the flow of heat and thermal. Then entropy, the dispersal, which talks about how heat goes from hot to cold. So this part is like the repetition of what we already know. We say the conservation of energy and energy conservation. Are we saying the same thing, or does it appear like tautology? Yes, it appears so, but we just want to use this to emphasize a law and use this to emphasize an action. Okay? So that's why it's sounding the way it's sounding, the conservation of energy and energy conservation. Reading the topic, you say, are they not saying the same thing? But they are emphasizing different aspects. So, like we know that the law of energy or conservation of energy says that energy cannot be created nor destroyed, but it goes from one form to another. So if we already know that energy cannot be created nor destroyed, so why are we thinking in terms of conserving energy? What do we really mean when we say we are conserving energy? You know, in some homes, they'll tell you, turn off the heater, turn off your lights, save energy, you're not there. Why did you leave it burning? All those stuff. Conserve the energy. What does that statement really mean? So the energy, we know it's not lost. Yes, in some cases, we tend to say like we lose energy to thermal heat because it's not going to be reversible and all that. But we know from the conservation law that it's not lost. There can actually be a process in place that will make such a system go a full circle, like we have seen in the heat engine. Yes, energy can be, the thermal can go to the environment, but we'll have a process that helps us keep the temperature at a constant rate in place. That is what we mean when we say we are conserving energy. We put processes in place that keeps that system at a constant rate. So the best way to describe that energy is conserved is to concentrate on the word efficiency. And what we do when we want to conserve energy is to think of what pays us most. How does it profit us? What can we put in to give us a bigger output? So we saw the bulb, like I said earlier, we saw more efficient car, energy efficiency, television, and so on and so forth. It is the idea of conserving energy that helps us advance technology from the understanding of entropy, that is dispersal and use of energy in terms of thermodynamics as well. Because relating thermodynamics also, when you talk about conversion of energy from one form to another, you will not only be staying with thermal energy, it advances beyond that. When you bring in some parts like electrical energy, you manipulate the system to yield a better result. Okay, so but the understanding of that is what bettered those technologies. The principles remain the same. When you understand it, you can actually modify them. So how do we use energy or describe entropy as it relates to life? Most people argued at the initial that the living organism tend to violate the rule of thermodynamics, that especially in terms of the second law. They tend to say stuff like, if the second law is described or basically primarily with the street language as running down, that is losing. But we look at life, we see that it appears like when you put in a little, it expands. How then does second law, which is the law that talks about dispersal, applies to life? Does it really work? So that was the question that bettered also the understanding of interpreting second law using entropy term and describing them to how the human make use of this in our everyday life. So the understanding also of how energy is converted from different forms helps with the understanding to answer the question that is it really the violation of rules, or it's actually adapting or adjusting or emphasizing, establishing the rule. So they notice that when they plant a seed, it grows into a complex entity. You planted a seed, it becomes a tree that can lead to multiple seeds that was planted. And then we see the process of fertilization leading to an adult human. We see billions of evolution in unicellular organisms, okay, billions of years, and they form complex things that we see today. And we see these processes that when you put in small, it yields bigger outcome. And then they're saying in such a case, we cannot use the law that says it's reducing or spreading out because it's multiplying instead. But really, the human process describes this better to establish the principle of second law of thermodynamics. So let's look at how that we have the thermodynamic view of the human body. When you eat, we already know, we have mentioned it several times, that what you get from the food you eat, they are called the chemical energy. All right? You eat something, you are taking in energy into the body. The human body is a closed system, isolated system. All right? So activities go on within the body that will bring about the giving off of heat to your environment. Okay? So energy leaves your body mostly in terms of heat to the environment. It means that the entropy of the environment will increase because you are giving to the environment. Remember when we said the signs for heat, when the system gains, is positive, when it's losing, it's negative. So the heat is leaving your system, you have the negative sign of heat and increasing the one in the environment. So you see that actually the process of developing, growing, evolving of organisms and all that is, am I the one writing this? Amaka, what are you doing?
Oh, sorry, I didn't know.
Okay, but how come you could influence my screen? All right, that aside. So it's good that you can write. So when we are looking at a revision class, some of you can come on to solve some problems, all right? So practice more on that which you just did and teach some persons how to do that so that our class will be more interactive. All right, so let's proceed. The processes that were described as multiplication were actually processes that established the principles of thermodynamics. We see When we grow, develop, we take in high quality and then a low entropy because we're giving out little heat that is not causing so much change to our environment, right? That's what we described as the low entropy in the form of food that we eat and from sunlight, and then we exhaust them, we give them out. That's what I mean by exhaust, as thermal energy to our environment. So those processes actually is taken from the environment. There is no way a growth process can be described without taking from the environment. In terms of plant, it's taken from the sunlight, it's taken from different sources to bring about such growth, so that when those sources are terminated, that terminates the growth. If you put a seed in the soil, you don't put water, you don't allow light, the sunlight to come on it, that which they term as multiplying will not happen. So that growth is actually transforming or converting energy to bring about what they are seeing as multiplication or growth. So it still answers or adjusts to the system or the principle of transforming energy from one form to the other. So the entropy of that system can also be described because it can either be high or low depending on how we are applying them. So this continuous exchange with the environment makes the increase in entropy. That's what makes the life real. So in reality, those processes are actually going on without violating the physical law in any way. Now, the physical laws, can they be violated? Yes, they can. But when you look through what we think is the violation process, it's going to eventually be described better in terms of transformation of energy. Okay. So that answers the question of entropy and life. So we'll move on to the very last part, which is entropy, free energy, and spontaneity. The only new thing we brought in here is the free energy and then spontaneity. We have seen spontaneity before when we described the irreversible process, okay? And this, when we go further, those of you in chemistry will really understand what is going on here. We describe or do chemical analysis reaction with the focus on what we call the Gibbs energy. The Gibbs energy has the symbol G, that is the G here, and it is equal to enthalpy minus temperature, and S is entropy. Okay, so we see that the Gibbs energy relates, bring in the concept of entropy, and that is why it came in here: entropy, free energy, and spontaneity. Now, the principle of the analysis reaction says that the requirement for a spontaneous reaction is that change in Gibbs energy must be less than 0. Okay, so whenever we want to describe reversible and irreversible process, we want to understand the energy exchange in such system, we apply this rule that Gibbs energy is going to be less than 0. And to apply Gibbs energy, you have to understand the enthalpy, which is H being equal to energy plus the product of pressure and volume. Okay, so to expand also the Gibbs energy, the Gibbs free energy, energy will be considered pressure, volume, entropy, temperature. You see all the parameters that we use to understand the description of transformation in reaction analysis. So when we say when you eat food, it transforms, it gives you energy, it does all that, we have factored these parameters into those statements. We just give you the statement, but the nitty-gritty of the calculation is what we just keep out so that we'll not be bugging you and scare you away from physics. Okay, so at this level, we just stay with the statement that we have what we call gives energy, and it is used to describe the reaction analysis. Just note those words. And it gave us a principle that the spontaneity for any reaction to happen, the G must be less than 0. And if G is less than 0 given this equation, it simply means to make that less than 0, the parameters on this side have to go high, right? So by second law of thermodynamics, the process of spontaneity therefore tells us that this will require an increase in entropy. And when we say increase in the entropy, we are talking about increase in the entropy of the universe. So if we use change in S, entropy is S. We use change in S, that's change in entropy of the universe, to be greater than 0 and give free energy less than 0, we can have the spontaneous reaction, okay? So the reaction can occur spontaneously if there's an overall increase in entropy. So Gibbs energy happens as a result to this, that is spontaneity, okay? So now going further to understanding the spontaneity, we see that, recall these two, Gibbs energy is less than 0. For this to happen, there will be increase in the entropy of the universe. And the entropy of the universe is actually the sum of the chemical entropy and the environment. All right. So if this is the sum, the entropy of the universe is the sum of these two, therefore we can express it that the entropy of the universe, which is these two, must be greater than 0 for spontaneity of reaction to occur. All right. So if the environment receives heat, which we use the symbol for heat is Q, received by the environment at certain temperature, the entropy will change, right? We said that we can also change entropy when we increase temperature or increase heat in the system. So if we bring that statement, which tells us that the entropy of the environment is given by the heat to the environment at certain temperature, and we substitute this back into that equation with the understanding that the temperature when it gains heat is a system is also losing chemical heat. That is like the human, if you give out heat to the environment, that heat that you are giving out is actually coming from the chemical energy from the food you ate, right? So if we combine these two, we can actually substitute into what the first equation means. That is this expression. Environment being Q over T. And we see that the Q is actually minus the heat from the chemical process. Substituting this for that Q, we'll have the entropy of the your system minus the heat. Looking at this expression, we're actually trying to express this in terms of chemical reaction, okay? We said reaction analysis, and that is why we are just going this route. So you see how that we are converting that of the environment to expressing it in terms of heat from the chemical processes, okay? So we will have the final expression of the increase in entropy to be of this form. So gives free energy is less than 0, increase in entropy is greater than 0. That's all what we've been saying. These equations are just equations that we use to analyze reactions or chemical reactions. So we stated that the second law requires spontaneity to happen. And if we write this in terms of the chemical involvement in the reaction and in temperature, we'll bring in this expression that Q is actually, which is the normal expression, heat is actually equal to change in enthalpy. And we have already defined enthalpy of a system as the energy plus the product of pressure and volume, right? Remember that definition of enthalpy. So this is actually what change in heat or chemical change in enthalpy talks about, that heat, chemical heat that is put in that system. All right, so if this is true and we can substitute into this equation, we can substitute this into this, we will have the expression again of entropy of the universe that have to increase to be this. So modifying this, that is make this the subject of formula, put this equal to 0 cross multiply, we will have this expression that is this. And it is this expression that we gave to us earlier, that this free energy is equal to H minus Ts. Okay, so we see that the expression H minus Ts, which is described as given free energy G, is going to be less than 0. From this expression, we got this. Okay, so this simply emphasizes the fact that the second law requires gives free energy to be less than 0 for spontaneity to happen, and the entropy must increase and cannot decrease. It means it is not reversible. Okay, do we have questions? We have summary of what we have done. Just go through them. We have the practice question as well. I'll be putting up the assignment at the end of the day, so look out for it, the assignment for this chapter. All right. Do we have question, comments?
Nope, sounds okay.
Yeah. So you said in an isolated system, entropy can only increase. If entropy is defined as the number of possible states of a system, how does that work exactly?
Okay, in this last part, I said that for spontaneity, the spontaneous process, the entropy must increase and cannot decrease.
I know that's not quite what I meant. I was talking about the definition in an isolated system, entropy can only increase. How does entropy increase in an isolated system?
Okay,
Like
what is said about isolated system is that the entropy of an isolated system will not decrease.
Yeah.
Will not.
So it can increase?
It cannot increase. It's an isolated system. It tends to be constant, like constant.
It's constant. Okay.
Yeah.
Okay. That makes sense to me, because it seems that there's a constant number of particles and a constant number of locations, and there could only be one level of entropy.
Yeah. So it's not. It cannot go down. It stays where it is.
Okay. Thank you.
Okay. Thank you so much. All right. That's the only question. If you remember, or when you're reading, you think about a question you want to ask, you can send me the email about it. If we have to schedule a Zoom meeting, we will. If we have to schedule to meet in person, we'll also do that to clarify things, okay? And somebody asked me if the exam is going to be concentrated on the part we are just doing now. No, the exam is going to be comprehensive. So it's going to go from what you have done from chapter 1 to chapter 13, okay? But before then, we'll have like a brief of what to expect. But the exam is not going to go out of what you already have. You just have the notes, the examples, the assignment. Just go through them and you're good. All right. Okay. In that case, no more question, comments. Well, have a great day. Have a great weekend. Bye-bye.
All right, thanks. Bye.
Yep.